Look at the stress fracture on this beam.
Noted. It's worse than we thought.
Ensure the casings are sealed properly before transport. One breach could compromise the entire sector.
We've doubled the inspection rate, sir.
The situation in the Pacific is deteriorating. We must secure these chemical supplies or face severe shortages by the third quarter.
January 1942. Dawn breaks over an American industrial landscape far from any front line. Snow settles on rail yards in Ohio and Pennsylvania. Factory whistles sound, but inside the warehouses, something essential is missing. The United States is at war. Battleships burn in the Pacific. Convoys assemble in the Atlantic. Artillery units train across vast fields. Every plan, every strategy, every movement of men depends on a simple, violent certainty: explosives. Yet, deep within procurement offices and War Department reports, an alarming truth circulates in quiet memoranda. America's traditional sources of gunpowder are under strain. Cotton linters, nitrates, chemical precursors, materials once taken for granted, are suddenly scarce. Shipping lanes are threatened. Stockpiles drain faster than they can be replenished. No headlines announce the danger. No public speeches acknowledge it. But without propellant, rifles fall silent. Without explosives, shells become inert steel. And without immediate solutions, industrial superiority means nothing. In this moment of pressure, far from the battlefield, the war turns toward laboratories, grain silos, and chemical plants, toward an unlikely idea growing in America's fields, waiting to be transformed. The reason for this crisis did not emerge overnight. It was shaped by years of assumptions, dependencies, and a world sliding steadily toward total war. Long before America entered the Second World War, its explosive supply system had been built on confidence rather than urgency. The United States emerged from the First World War with a reputation for industrial might, but also with a dangerous assumption that the next major war, if it came at all, would arrive slowly. In 1918, American factories had produced enormous quantities of smokeless powder and high explosives. Plants operated by companies like DuPont and Hercules expanded rapidly under wartime contracts. When the armistice came, production collapsed just as quickly. Facilities were downsized, mothballed, or repurposed for civilian chemicals. Stockpiles were reduced to what planners believed was a prudent reserve. Throughout the 1920s and 1930s, military procurement budgets shrank. Congress, wary of war profiteering scandals from the previous conflict, imposed tight oversight. The Army and Navy maintained small standing forces, and with them, modest ammunition requirements. Explosives were produced steadily, but conservatively, enough for training, testing, and limited contingencies. The chemical foundation of American gunpowder remained largely unchanged from World War I. Smokeless powder relied on nitrocellulose, a compound derived primarily from cotton linters, the short fibers left on cotton seeds after ginning. Combined with stabilizers, plasticizers, and nitroglycerin in some formulations, nitrocellulose formed the backbone of modern propellants. High explosives depended on nitric acid, sulfuric acid, and refined cellulose, all of which required substantial industrial infrastructure and reliable raw materials. This system worked as long as supply chains remained calm. Cotton came from domestic farms. Chemical precursors moved freely by rail and ship. Imports of specialized nitrates supplemented domestic production. There was no immediate pressure to innovate, no reason to question whether traditional materials might one day become insufficient. Even as war erupted in Europe in 1939, American planners believed time was on their side. The Neutrality Acts limited arms shipments. Rearmament moved slowly. Though President Roosevelt pushed for preparedness, the scale remained cautious. Ammunition plants expanded, but not at the pace seen in Britain or Germany. Explosive production rose, but it did not yet strain the system. Behind the scenes, however, cracks were forming. Global nitrate markets tightened as European powers diverted resources inward. Shipping lanes grew more dangerous. Britain, cut off from continental supplies, began sourcing aggressively from the Americas. The same raw materials used in gunpowder were also essential to fertilizers, plastics, and industrial chemicals, creating competition within the civilian economy. The Hercules Powder Company stood at the center of this industrial web. Founded in 1912 after the breakup of DuPont under antitrust law, Hercules had inherited much of DuPont's explosives expertise. By the late 1930s, it was one of America's primary producers of smokeless powder, dynamite, and industrial explosives. Its engineers understood nitrocellulose, nitration processes, and large-scale chemical safety better than almost anyone in the country. Yet even Hercules operated within the same assumptions as the War Department. Production forecasts were based on limited engagements, not global conflict. Plants were efficient, but not designed for the sudden multiplication of demand that total war would require. Everything changed on December 7th, 1941. The attack on Pearl Harbor transformed American industrial planning overnight. Mobilization orders surged through Washington. Ammunition requirements were recalculated not for months, but for years of sustained combat across two oceans. Artillery shells, naval rounds, aircraft ammunition, each demanded precise, reliable propellants in unprecedented quantities. Within weeks, War Production Board reports began to show alarming curves. Consumption outpaced production. Reserves fell. And at the base of it all lay a simple truth. The raw materials feeding America's explosive industry were finite, fragile, and suddenly contested. The problem was no longer theoretical. It was immediate, measurable, and spreading through every branch of the armed forces. That pressure would only intensify as 1942 unfolded, forcing planners and chemists to confront the full scope of what modern war demanded and what the existing system could no longer provide. By early 1942, the scale of America's explosive requirements had become staggering. War plans were no longer abstractions drawn on maps. They were production schedules measured in tons per day. Every artillery division required millions of rounds annually. Naval engagements consumed powder at a rate unseen in peacetime calculations. Aircraft armament multiplied the demand further. Each machine gun belt and autocannon drum feeding on precisely formulated propellant. The War Production Board, established in January 1942, began issuing directives that reflected a brutal arithmetic. Output had to increase not by percentages, but by multiples. New ammunition plants were authorized. Existing facilities were ordered to run continuously. Safety margins that had once allowed careful pacing were compressed under wartime necessity. Almost immediately, bottlenecks appeared. Cotton linters, the backbone of nitrocellulose production, were in shorter supply than planners had assumed. Cotton itself was abundant, but linters required specialized processing. They were also used in civilian products, film, lacquer, plastics, industries now competing with the military for the same fibers. Converting agricultural output into usable explosive-grade cellulose was neither quick nor flexible. Nitric acid posed a parallel challenge. Its production depended on ammonia, sulfur, and extensive chemical infrastructure. While the United States possessed significant capacity, it was not infinite. fertilizer production, essential for maintaining agricultural yields during wartime, drew from the same nitric acid base. Diverting too much risked long-term food shortages, an unacceptable trade-off. Shipping constraints compounded the problem. Rail networks were congested. Ports prioritized finished munitions over raw chemical imports. German U-boats disrupted Atlantic traffic, limiting access to supplemental materials from abroad. Even domestic transportation struggled under the weight of simultaneous mobilization in steel, fuel, and machinery. At a molecular level, gunpowder was unforgiving. Smokeless propellants required cellulose chains of specific length and purity. Impurities caused instability. Variations altered burn rates. In artillery, inconsistency could mean inaccurate fire or a catastrophic failure. There was little room for improvisation. Yet improvisation became unavoidable. Within technical committees and classified memoranda, chemists began revisiting questions that had once seemed academic. Was cotton truly the only viable cellulose source? Could alternative carbohydrates be converted into nitrocellulose with the required properties? What mattered most, the origin of the cellulose or its final molecular structure? The idea was not entirely new. Chemists had long known that cellulose existed in many plant forms. Wood pulp, straw, and agricultural byproducts all contained it. But converting these sources into explosive-grade material introduced complications. Lignin contamination, inconsistent fiber lengths, and processing residues posed serious risks. Corn, however, stood apart. The United States was the world's largest producer of corn. Its starch was chemically uniform, readily extractable, and already processed at industrial scale for food and industrial uses. Cornstarch consisted primarily of long chains of glucose, structurally similar to cellulose, though not identical. The question was whether it could be transformed, modified, and stabilized into a form suitable for nitration. For military planners, the idea bordered on desperation. For industrial chemists, it represented an opportunity rooted in logic rather than hope. The Hercules Powder Company was among the first to examine the possibility seriously. Its laboratories had experience adapting civilian chemical processes to military needs. Its leadership understood that failure was not merely a commercial risk, it was a national one. Pressure from Washington intensified. Contracts were rewritten. Timelines shortened. Solutions were expected, not requested. Some within the ordnance establishment doubted the feasibility. Explosives were not forgiving. A marginal propellant could destroy guns, aircraft, or lives. But the alternative, doing nothing, was equally dangerous. By the spring of 1942, experimental programs moved out of theory and into controlled trials. Corn was no longer just a crop. It was a strategic material under evaluation, its potential measured not in bushels, but in blast consistency and burn rates. The war had reached a point where victory depended not only on factories and soldiers, but on whether chemistry itself could bend under pressure without breaking. That question would soon be answered from multiple perspectives: human, industrial, technological, and strategic, each revealing how close America came to the limits of its own ingenuity. Inside Hercules laboratories and production plants, the war narrowed to benches, gauges, and sealed vats. Chemists worked under blackout curtains and security clearances that forbade even casual explanation. Many had joined the company in the interwar years, expecting stable civilian careers. Now their calculations carried lethal weight. Shifts stretched late into the night. Safety protocols remained strict, but the margin for delay vanished. Every failed batch meant lost time. Every successful test brought quiet relief, never celebration. These were not dramatic moments, but cumulative ones. Progress measured in decimals, in pressure tolerances, in burn curves traced on paper. Plant workers faced risks that rarely appeared in newspapers. Nitro compounds were unforgiving. Static discharge, temperature fluctuation, contamination. Any could trigger disaster. Yet absenteeism remained low. Many workers had sons, brothers, or husbands already overseas. The connection was understood without speeches. This powder would travel where they could not. Hercules facilities were not built for experimentation at scale. They were designed for proven formulas, repeated reliably. Converting sections of plants to handle alternative feedstocks meant redesigning processes midstream. Storage systems changed. Milling methods adjusted. Waste streams recalculated to avoid contamination. Coordination with the War Production Board added pressure. Output targets rose, even as procedures evolved. There was no pause between research and production. Once a process showed promise, it moved immediately toward industrialization. This compressed timeline blurred the boundary between laboratory science and factory labor. Decisions once reviewed for months were approved in days. Far from the plants, Midwestern cornfields took on new significance. Cornstarch processors, accustomed to supplying food and paper industries, received classified contracts. Rail cars loaded with refined starch moved under military priority. Farmers never saw the end product, but their harvests fed an unseen front. War transformed corn from commodity to component. Fields, silos, and refineries became quiet extensions of the arsenal. Together, these human, industrial, and agricultural pressures converged toward a single unresolved question. Could theory withstand reality when lives depended on it? At the core of the problem lay chemistry, stripped of abstraction. Cornstarch was not cellulose. It was composed primarily of amylose and amylopectin, glucose polymers arranged differently from the fibrous chains found in cotton. To become usable in propellant formulations, these molecules had to be transformed, their structure modified without introducing instability. Hercules chemists focused on controlled derivatization. Through hydrolysis and repolymerization, starch-based materials could be altered to approximate the functional behavior of nitrocellulose. The nitration process itself demanded precise acid ratios and temperatures. Too aggressive, and the compound degraded. Too mild, and the energetic yield fell short. Early tests revealed promise. Burn rates could be adjusted. Stability under storage improved with proper plasticizers. Most importantly, ballistic performance fell within acceptable military tolerances. These were not ideal substitutes, but they were reliable. From a strategic perspective, the implications were immediate. Corn was domestic, renewable, immune to naval blockade. Every ton of cornstarch derived explosive reduced dependence on vulnerable supply lines. It also freed traditional materials for applications where substitutes were impossible. Quietly, this adaptability reinforced Allied resilience. Britain and the Soviet Union faced far harsher material constraints. America's ability to solve internal shortages preserved its role as the arsenal of democracy, not through brute force alone, but through flexibility. Axis intelligence focused on visible outputs, ship counts, aircraft numbers, steel tonnage. Chemical substitutions left few signatures. No new factory silhouettes betrayed the shift. No captured document revealed cornfields feeding artillery. German planners continued to underestimate American endurance. They saw production curves, but not the improvisations beneath them. By the time U.S. firepower surged across multiple theaters, the underlying vulnerabilities had already been sealed. With technology proven, strategy aligned, and secrecy intact, the The final test remained unavoidable: whether these new explosives could perform under the unforgiving conditions of war. That reckoning would arrive not in theory, but in production lines, inspection reports, and ultimately, live fire. By mid-1942, the work at Hercules crossed a line that could not be reversed. Experiments gave way to production trials. Controlled batches of cornstarch-derived propellant moved from laboratory glassware into industrial mixers, drying rooms, and pressing equipment designed for traditional powders. From that moment on, success was no longer academic. It would be measured by whether guns fired or failed. The first large-scale runs were deliberately conservative. Output was slow. Inspectors from the Army Ordnance Department monitored every stage. Samples were sealed, labeled, and shipped to proving grounds under guard. There, the powders were subjected to standardized tests: pressure curves, temperature sensitivity, storage stability, and ballistic consistency. Failures came early. Some batches burned unevenly. Others produced acceptable muzzle velocity, but left excessive residue. In artillery, residue meant fouling. Fouling meant degraded accuracy. In worst cases, it meant danger to the crew. Each failure sent data back to Hercules, where formulas were adjusted and processes refined. Time pressed constantly. The Pacific War intensified. North Africa loomed. Ammunition expenditures climbed faster than forecasts. Yet the War Department resisted lowering standards. A marginal propellant could cost more lives than it saved. Gradually, the reports changed tone. Pressure curves flattened into acceptable ranges. Storage tests showed stability under heat and humidity. Weapons fired thousands of rounds without abnormal wear. In controlled firings, cornstarch-based powders performed alongside conventional formulations without visible distinction to the crews operating the guns. By late summer, federal inspectors approved limited operational use. This approval did not arrive with ceremony. It came as typed authorization, stamped and distributed under classification. But its implications were profound. For the first time, America's explosive supply no longer rested entirely on cotton fields and vulnerable chemical chains. A substitute had crossed the threshold from possibility to reality. Production expanded immediately. Modified processes were integrated into existing lines. Cornstarch shipments increased. Output numbers climbed. Not explosively, but steadily, reliably, enough to stabilize the curve that had threatened to dip in a crisis. Yet one final barrier remained. Laboratory and proving ground success did not guarantee battlefield reliability. These powders now had to survive transport, storage, and combat use across oceans and continents. The moment of truth would come not in reports, but in sustained wartime deployment, where chemistry met chaos and there were no second chances. The transition from approval to integration unfolded quietly, without announcement or celebration. Ammunition loaded with cornstarch-derived propellant entered the supply system indistinguishably from conventional rounds. Crates were stamped, sealed, and shipped alongside millions of others, bound for ports, depots, and forward bases whose commanders never knew the chemical story inside. In the fall of 1942, as American forces landed in North Africa under Operation Torch, artillery units fired relentlessly to establish beachheads and break resistance inland. Ammunition consumption surged exactly as planners had feared months earlier. Yet no sudden shortages followed. Guns remained supplied. Fire missions continued without interruption. Across the Atlantic, naval gunners engaged U-boats with depth charges and deck guns, expending propellant in constant patrols. In the Pacific, Marines trained and fought under tropical conditions that punished unstable explosives. Storage magazines baked in heat and humidity. Rounds were moved, dropped, and fired under stress. Reports returned not with alarm, but with silence. Silence, in this case, meant success. Weapons functioned as designed. No abnormal misfires. No pressure-related failures traced to propellant composition. For ordnance officers, this was the highest form of validation. The substitute had become invisible, its presence no longer noteworthy, its performance routine. By early 1943, production figures told the fuller story. Hercules and associated plants delivered explosive output at levels that would have been impossible using traditional materials alone. The fear bottleneck never fully materialized. Instead, capacity expanded in parallel with demand. The war's tempo accelerated. American firepower grew not in bursts, but in sustained force. The industrial gamble taken months earlier now underwrote every major operation, from the Mediterranean to the Central Pacific. What might have been a crippling weakness became a stabilized foundation. The turning point did not announce itself with a single explosion or battlefield victory. It revealed itself through continuity, through the absence of breakdown, through the steady roar of guns that never fell silent. And as the war pressed forward, the consequences of that quiet success began to ripple outward, shaping not only the conflict's logistics, but its long-term industrial and strategic balance. By the end of 1943, the scale of America's explosive output had reached levels unmatched in its history. Ammunition plants operated around the clock, feeding campaigns across Europe, the Mediterranean, and the Pacific. Behind these numbers lay a less visible transformation, one that insulated production from collapse at its most vulnerable point. War Production Board summaries showed stabilized propellant supply curves where early 1942 projections had predicted shortfalls. Cotton linters remain important, but no longer singular. Nitric acid allocation balanced more effectively between explosives and fertilizers. Rail congestion eased as sourcing diversified and pressure on specific routes declined. The contribution of cornstarch-derived explosives was not isolated in public statistics. It was embedded in totals, folded into tonnage reports and quarterly outputs. But internally, ordnance analysts understood its significance. Alternative cellulose sources had bought time to expand traditional capacity, time to train labor, time to secure logistics. Operationally, this stability mattered. Artillery doctrine relied on sustained fire, not brief engagements. Naval warfare demanded constant readiness. Aircraft armament required absolute reliability. The absence of ammunition rationing allowed commanders to plan aggressively, unconstrained by fears of industrial exhaustion. Allied partners benefited indirectly. Lend-Lease shipments flowed with fewer interruptions. Britain and the Soviet Union received munitions produced in an American system that had quietly removed one of its most dangerous choke points. The result was not dramatic innovation, but resilience, a quality less visible than firepower, yet equally decisive. By ensuring continuity, Hercules and its peers helped convert American industrial capacity into operational certainty. But the effects did not end with wartime numbers. As victory drew closer, the implications of this adaptation began to extend beyond immediate military necessity, shaping the post-war industrial world. When the war ended in 1945, America's explosive plants did not simply shut down. They decelerated, transitioning from emergency output to peacetime production with a depth of experience that had not existed 4 years earlier. The cornstarch-derived processes developed under pressure became part of a broader legacy of chemical flexibility. Hercules emerged from the war transformed. Its wartime role had expanded its expertise in polymer chemistry, process control, and large-scale adaptation. Techniques refined for explosives found application in plastics, coatings, and industrial materials that would define the post-war economy. The boundary between military chemistry and civilian industry blurred permanently. Agriculture, too, felt the aftershocks. Corn had proven itself not only as food or feed, but as an industrial resource. This realization accelerated research into bio-based materials in the late 1940s and 1950s. While explosives faded from public view, the idea that crops could underpin advanced manufacturing endured. Strategically, the lesson was absorbed by military planners. Dependence on single-source materials was recognized as a vulnerability. Redundancy, adaptability, and domestic sourcing became guiding principles in Cold War logistics. The memory of 1942 lingered in procurement doctrine, even as the details remained classified or forgotten. Public memory, however, moved elsewhere. Battles, generals, and weapons systems dominated narratives of victory. The quiet crises solved in laboratories and factories rarely entered popular history. Yet without those solutions, battlefield success would have been impossible. The war had proven that industrial conflict was not decided solely by who possessed the most resources, but by who could reshape them under pressure. That realization invites reflection, not on explosions, but on the unseen ingenuity that sustained them, and on how close the outcome once came to being decided far from the front lines. In the popular memory of the Second World War, victory is measured in landings and offensives, in ships launched and cities liberated. Yet beneath every visible moment lay systems that rarely appear on maps. Quiet solutions, invisible decisions, chemical formulas written under pressure, far from gunfire. The crisis of 1942 revealed how modern war tests more than armies. It tests assumptions. America did not run out of courage or manpower. It nearly ran out of materials it had always believed would be there. The response was not desperation, but adaptation, an industrial culture willing to rethink fundamentals when tradition failed. Cornfields never heard artillery. Farmers never saw the proving grounds. But their harvests moved through refineries, laboratories, and factories, becoming propellant that powered rifles, guns, and shells across the world. War turned abundance into advantage not through force, but through understanding. Hercules and its chemists did not win battles. They prevented silence. They ensured that when orders were given, weapons answered. Their achievement was measured not in spectacle, but in continuity, in the steady, reliable presence of firepower when it mattered most. History often remembers the moment of impact. Less often does it remember the moment of prevention. Yet in 1942, the ability to prevent collapse proved just as decisive as any battlefield triumph. In that sense, the war was shaped not only by steel and strategy, but by chemistry and choice, by the recognition that survival in total war depends on the willingness to see familiar things differently, even something as ordinary as corn, when the fate of nations hangs in the balance.